Welcome, everybody. Happy New Year 2026. This is the first talk of the new semester of the new year given by David Stanovsky of Charles University on the enumeration of groups and quasi-groups and semi-groups and quandles. Please, David.
Right. Thank you for invitation and for the introduction. I wanted to tell you something about enumeration of algebraic structures, which is a topic I've been interested recently, and I chose essentially two subjects. One is classical. I want to talk a little bit about enumeration of groups and related structures, and in the second half, I want to tell you something about the class that I'm interested in as my research project, and that's the class of quandles. And I want to show some similarities between the two enumeration quests, and maybe let you think about whether there is a common framework which could sort of predict whether there are plenty models in a given class or few models in a given class. I don't know. I don't even have conjectures, but I have some data to present and to think about. So enumeration of algebraic structures up to isomorphism is, I think, a very classical subject. I guess everybody knows the online encyclopedia of integer sequences, and the very first sequence with number 1 is actually enumeration of groups. And this is the table that you can compile. It's enumeration of groups up to 100, and the state of the art is enumeration groups up to 2047. So it's just a fragment of it. And maybe if you look at it for the first time, it looks chaotic, but indeed there is some structure in the table. There's a lot of small numbers, but there are also occasional large numbers, which and the large numbers appear at numbers which have many prime divisors. So I guess everybody knows that. It looks like there are relatively few groups of a given order, right? Which is maybe a naive observation from such a small sample. As we shall see, it's a wrong observation, but let's see how it compares to other types of structures. So on the other extreme, you could just consider binary algebraic structures, a set and a binary operations. Also, let's call it shortly a groupoid. And natural question, how many groupoids are there of order n up to isomorphism? And again, you see that the number of the sequence is 1329, so it's one of the first sequences that was ever entered in the online encyclopedia. And it grows a lot, which is, I guess, no surprise, right? Maybe slight surprise might be how do we actually get these large numbers, right? How do we know the precise number of groupoids of order 8 up to isomorphism? But that's a different question. So what about some intermediate classes, right? Quasi-groups, semi-groups. So I'm not sure if it's supposed to be obvious that there are many quasi-groups. To me, it's not entirely obvious. So there, I mean, the groupoid sequence grows faster, but this one grows also kind of fast. What about semigroups? In my opinion, it's less of a surprise that there are plenty of semigroups, but actually the numbers are smaller than for quasi-groups, which I don't know. Again, I don't know. Should it be surprising? Shouldn't be so surprising. This is what you can calculate with certain techniques. And the question is obviously how fast does it grow? What is the asymptotic behavior, upper bounds, lower bounds? So let me start with some observations. So there is an obvious upper bound on the number of groupoids, right? On the number of binary operations, which is n to n square, simply the number of multiplication tables. And there is the obvious lower bound. right? Only n factorial group points can be mutually isomorphic. So there is a lower bound given by the total number of multiplication table divided by n factorial, which gives you a relatively tight bound on the number of groupoids. So n to n square is essentially both the upper and lower bound, right? So what about say semigroups, right? So let me first talk about semigroups. So it seems to be a folklore result, or at least I could not find anybody to attribute this construction. So there's a lot of semigroups, like almost as many as there could be. So it's the lower bound is n to 1 minus epsilon n square, where so in what sense epsilon, whichever epsilon you choose for all n bigger than some threshold, there are at least n to 1 minus epsilon n square semigroups up to isomorphism. And the construction is actually relatively simple. So this is the multiplication table of the semigroup. So say the semigroup has n elements, and m is a parameter, and in three of the four quadrants you put one, and in the other quadrant you put just any set of numbers which is at most m. And it's easy to check that this is always an associative operation. And if you optimize m to obtain most of the multiplication table, then you actually obtain the result. I mean the lower bound that I mentioned. So the construction is not really complicated, and of course in semigroups there is some combinatorial explosion. I mean, as it's not so difficult to make an operation to be associative, and there's still a lot of freedom to put pretty much anything in part of the table, so there's plenty of models. For quasi-groups, this trick is much more difficult to make work, right? There's way more constraints when you want to make a Latin square. So again, there's pretty large lower bound. It's substantially smaller in the sense that there is one half in the exponent, so it's n to one half of n square minus something small. But the construction is difficult. So the construction, I mean, this lower bound was achieved by Marshall Hall in 1940s, and it's not easy to explain. And there are better lower bounds, but this is the first results which shows that there's a lot of quasi-groups. So these are some sort of structures that admit some combinatorial constructions, right? You can get a lot of semigroups by filling a big part of a table by some triviality. You can get a lot of quasi-groups actually by exchanging elements so if you have a quasi-group, then you can tweak the multiplication table just a little bit and get a different one. And I'm not sure that this is Marshall Hall's construction, but that's a way you can often construct a lot of quasi-groups. In groups, this like local change of the multiplication table is certainly not. I'm not sure. I don't want to say not possible, but certainly not easy, and I think in some sense it's close to impossible. Back to groups, right? So how many groups are there actually? So I printed the table slightly larger, up to 300. And of course, you can, I mean, many of the numbers are very small, right? I mean, there's a single group of prime order. There are just two groups of prime square order. There's, for instance, just very few groups of well, I mean, if there are few prime divisors, then there are very often very few groups. but some of the numbers are pretty large, right? So the largest in the table is this one, which is 228, 256. So maybe, uh, we can also draw a plot. So especially the right part of the picture is interesting in this sense. To estimate how the numbers grow. It's a logarithmic plot of the whole range for which the numbers are known, so up to 2047. And on the vertical scale, you have logarithm of the number, right? So you see that actually for powers of two, the number of groups grows relatively fast, right? It's maybe not exponential. If it was exponential, it would be approximable by a line, right? So it doesn't seem so, but still it grows pretty fast, right? So let's print just enumeration of groups of order 2 to n. And again, like looking at the number of the sequence in the OIES database. You see that this is one of the first sequences ever entered in the database, and again, it looks like it grows pretty fast, right? So how fast? I mean, is it exponential? It doesn't seem to grow as fast as like the number of quasi groups, right? But grows relatively fast. But it's actually somewhat misleading, right? Because I have essentially logarithmic scale on in the sequence. So let's normalize. So this is log 2 of the number of groups of order 2 to the n. And now the question is how fast, if you can predict how fast this sequence grows. It looks a little bit is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is a little bit more than 11, right? It almost works, sort of. So if it was Fibonacci sequence, then the growth would be exponential. So this is a little bit less. So now it's a meaningful question. I mean, how fast is the growth of this sequence, right? So here comes difficult mathematics. So the bounds are known. Uh, and this is a summary of the results, which explains the growth of the sequence. So it's a so classical results from I mean the big the first substantial part of the theory comes from 1960s. So in 1960s, they were able to calculate or to estimate the number of p groups. So the two main names are Graham Hickman and Charles Sims, who were able to obtain together tight bounds for for the enumeration of p groups. So first, so consider order of the group to be of the form p to k, and now, already Graham Hickman was able to prove that the growth is actually quasi-polynomial. It means more than polynomial, but less than exponential, and of a particular form. So it's the number of so when I write that symbol, then I mean the number of groups of order n, where n is prime power, is more or less, in a precise sense, to some constant times log n cubed, right? So it's more than any polynomial, but it's less than exponential growth. And what Hickman actually proved is a precise lower bound and precise upper bound. So the lower bound is achieved with the following formula. So it's essentially p2 k cubed. with the constant in the exponent to be 2 over 27. So how did he do that? So he had to construct a lot of p groups, and he found a particular construction taking a free group and factorizing over a subgroup generated by certain powers and commutators of a particular type. And in his construction, there are some parameters like the number of generators. And then he could somehow estimate the number of groups based on the parameters in his construction, and by optimizing to get the most groups, he came to the constant 2 over 27. So it became as a result of some optimization of parameters in some general construction. Graham Hickman was also able to obtain a precise upper bound, and again, it's cubic in the exponent, and the constant that he was able to obtain was 1 over 6. And how did he do that? So every E group has a subnormal series with cyclic vectors. And if you have a subnormal series with cyclic vectors, it's called, then there is a sort of generic way to create a presentation of the group. It's based on if you have the series, then you can create a presentation of the group. And it's called polycyclic presentation. And there's quite some theory about how these polycyclic presentations can look like. And there is even some isomorphism theory for these polycyclic presentations. So he was able to estimate to get an upper bound for the number of polycyclic presentations. So there's not that many ways you can create those, and a lot of those are actually give you isomorphic groups. So that's how we obtain the upper bound. And in fact, these polycyclic presentations are also used in enumeration of groups on a computer. So getting the multiplication in when you actually want to calculate the tables that I showed you, polycyclic presentations is one of the tools that's being used. So the work of Graham Hickman was followed by Charles Sims, and he was able to obtain a tight upper bound in the sense of the constant. So it turns out that this sort of ad hoc constant 2 over 27 that Hickman got as like a result of optimization of parameters in his construction is also an upper bound. But while the polycyclic argument is relatively simple, it's a couple pages. The Sims upper bound is very complicated. It occupies about a quarter of a book, and I didn't even try to read it. I have to admit, it's more complicated group theory than I can at the moment understand. So that's the case of P groups, and of course, like a naive idea, just looking at the data, is that there's way more P groups than other groups, but I mean, prove it, right? And the general result on the number of groups of order n was obtained by Laszlo Piper in 1993. And so he can prove what one would probably expect, that the upper bound for general groups is the same as for P groups. So it's also like well, cubic in the exponent, but of course you have to formulate it differently in case of general groups. So the precise formulation is here. But what I want to point out is that there is the same constant 2 over 27. So yeah, this sort of confirms the idea that there are as many P groups as general groups, at least asymptotically. And again, this is a very complicated result. It occupies about half of a book. It's about 100 pages. And the book I'm actually referring to is a book by Blackburn, Neumann, and Venkatraman called Enumeration of Finite Groups. It's very nicely written. It has a very nice introduction. It has quite a few toy examples on like simple proofs, worse bounds, but something that you can learn from how the enumeration could possibly done. And so that's about the first quarter of the book, and then the remaining part of the book is the Sims and Piber's complicated work explained. So these are some classical results. Also, one could wonder how do you actually get these tables. So that's another story. The mathematician behind a lot of calculations about group is Derek Holt. He wrote a book that explains how these things are done. For key groups, some efficient handling of polycyclic presentations is the key, and for nilpotent groups, well, that's simple because they're just the direct product of p groups. And the fun starts with non-nilpotent groups. So there are some tricks for solvable groups, and there are some even more complicated and ad hoc tricks for non-solvable groups. And it only works because there are so few non-solvable groups up to order 2048 that you can sort of handle them using lots of ad hoc tricks. So that's very roughly speaking the state of the art. So the smallest number for which we don't know the number of groups, as far as I know, is 2048, and that's the p group case. So right. So that's. The first part of the talk, review of what we know about groups and how does it compare to, say, semigroups and quasi-groups, which seem to be related to groups, and there's way more semigroups and quasi-groups than groups, which is obvious, but like it's almost as many as we. All right. So now the second part of the talk. It's my favorite class of algebraic structures called quandles. So first I will introduce what the quandles are, and then I will talk about some enumeration results, both mine and mostly work of others. So what is a quandle? Again, it's a binary algebra, and it satisfies say two conditions. It's an idempotent algebra. X times x is x, and the principal condition is that all left translations are automorphisms. So it's a very symmetric structure. So there's a lot of automorphisms. So if you look at the multiplication table, what is a left translation? So it's just a row of the multiplication table. So all rows should represent a permutation, and this permutation should be an endomorphism of the structure, right? So very symmetric structures. You can write it equationally. You get three identities, which sort of resemble syntactically axioms of groups, but that's probably irrelevant. Yeah. So what's the motivation behind this class? Why do I study these? Quandles appeared in many instances in mathematics. Group conjugation is an example of a quandle. I will talk about it on the next slide. Affine forms can be used to construct quandles. One of the original motivations was the study of symmetric spaces, some concept in differential geometry, which is actually leads to quandles, which have a differentiable structure. In mathematical physics, so quandles are a particular type of solutions to the Yang-Baxter equation, for instance, and so on. Maybe the most well-known application of quandles, which you might have seen, is that with each quandle you have a knot invariant. So there are coloring invariants of knots. You might have heard about the three coloring of knots. You are coloring the arcs of a knot in a particular way. And whenever you can find a non-trivial coloring, then that's a proof that the knot cannot be untied. So here is just a motivating picture. You have a figure 8, which is colored by the quandle with 5 elements, where the operation is 2x minus y modulo 5. So the Fox coloring is actually a particular type of this quandle coloring. So that's maybe the main motivation. But I don't want to talk about that. That's sort of one thing that motivates why enumeration, because with each quandle you have a not invariant. So maybe if you have lots of quandles, you have lots of invariants, and you can do something with it. So that's a naive idea, but I think it serves as a motivation for quandle enumeration quite well. Examples. Let me tell you 2 examples. The first one actually plays some role in the enumeration quest. So, what is an affine quandle? You have an abelian group, and you take an affine form. It's a binary mapping 1 minus f applied to x plus f applied to y. What is f? F is just any automorphism of the group, right? Or you can look at it as a module, and it's a multiplication by 1 minus something times x plus something times y, right? So that's one type of quandles. So with each abelian group, you have quite a few of them, right? As many as is the size of the automorphism group. Which, however, is not terribly big usually. Conjugation quandles is another classical example. If instead of the group operation, you take the operation x, y, x inverse, you get a quandle. Why is it a quandle? Idempotence is obvious, and the left translations are actually the inner automorphisms of the group, right? So every inner automorphism it's an automorphism of the group, so it's also an automorphism of the derived structure, right? So these are just 2 examples. And so this is how you get from groups to quandles. With every group, you have associated quite a few quandles. But also, what is more important, the other way around, with each quandle, you have associated some permutation groups. And these permutation groups play an important role in the classification of quandles. That's a way to transfer properties of quandles into the language of groups, and then maybe prove something about quandles using group theory. So whenever you have permutations in your setting, it's natural to generate a permutation group out of those, right? So since all left translations are automorphisms, then just generate a subgroup of the automorphism group by those translations. This is called the left multiplication group. And also in the theory, the subgroup generated by so-called displacements, which measure how much do 2 translations differ. That's another group that plays a role in the structure theory of quandles. And a particularly interesting class of quandles is that of connected quandles when the multiplication group acts transitively. So again, one of the motivations comes from knot theory, because all meaningful invariants of knots actually, all meaningful quandle invariants of knots actually result from connected quandles. So when you have the knot theoretic motivation, you are more interested in the connected quandles. I will now show some enumeration results. They will regard quandles in general and connected quandles. Okay, so how does the sequences look like? So this is the enumeration of quandles. State of the art is the number of quandles up to order 13, up to 13 elements, and again, it grows substantially, right? It's certainly exponential. It doesn't seem to grow as fast as the number of quasi-groups or semi-groups, right? Just naive observation. So that's general class of quandles. Okay, but probably not surprising that there's a lot of quandles. I mean, the way that you can just compose a quandle out of a bunch of permutations, yeah, so there should be quite a few of them. Now, so what are the precise bounds? we know both lower and upper bound on the number of quandles. And again, first, there are two bounds with different constants. It's a result of Blackburn, which are the same Blackburn that wrote the book about enumeration of groups. So he's also got interested in this problem. And the lower bound means that you have to construct a lot of quandles. So he found some ad hoc construction which provides a lot of them. And again, the trick is that under certain circumstances there is quite some freedom in the multiplication table. It's sort of this like the construction for the semigroups. That's sort of construction, I would say. Yeah, you can somehow trick the fact that automorphisms are that translations are automorphisms, and I don't know. I cannot explain it without making pictures, but yeah, there's a combinatorial way to construct a lot of quandles with some trickery. The upper bound is trickier. So Blackburn figured out a useful representation of quandles that I will explain a little bit later. And uh, based on this representation, he was able to obtain upper bounds using some results from group theory. And the constant that he's got can be estimated like 1.56. So his argument is relatively short, and the constant is certainly not optimal, as he admits, and as in fact turns out it's not optimal. And the project was taken over by Ashford and Riordan, and they actually could prove that the constant 1/4 is right. It's essentially well, it's the same representation that Blackburn used, but it's much more complicated group theory around allowing to do much better estimates. So note that there's way more quandles than groups. Well, not surprising. So the number of groups is quasi polynomial, right? This is 2 to n square actually with some constant, but it's also way less than the number of semigroups or quasi-groups. Right? In that case, it was n2 constant times n square. Now we have just 2 constant times n square. So there's the growth is certainly slower. Do you find it obvious? I don't find it obvious. I don't know. Okay, so so one phenomenon that I'd like to eventually to see explained, if you can somehow predict whether the growth in your class will be as fast as it gets, like for semigroups, quasi-groups, or relatively slow, like for groups, or something in between, like for quandles. Is there some general framework that would predict that? So that's a question I'd like to look at in future. Right. So these are quandles in general. So they can. So if you look at the action of the multiplication group, then you can have as many orbits as you want. And of course, if you have lots of orbits, you have a lot of freedom in the multiplication table, and that's the Blackburn's construction. If you have just a single orbit of the multiplication group, then I mean, no surprise, the numbers will drop significantly. But what I find interesting is that actually this table resembles the one for groups, right? It's there's a lot of small numbers. There are some bigger numbers, and they appear, well, it's maybe not obvious because there aren't too many. I mean, the table is relatively small, but you can notice that the big numbers appear at powers of primes, like the 65 is of order 27. Where do we have 32? I think this is 32. Well, it's not so many, but okay, there's also a reason for that. So, so is it a similar behavior like for groups? Uh, well, in fact, I don't know. Um, you can okay. So these are connected quandles. You could say that this is still a bit too general structure. Like from the viewpoint of universal algebra, this is no good. It doesn't satisfy any Maltsev condition. So could have a feeling that you can have plenty of them. So a special case of quasi-group quandles. So it's at the same time it's a quandle and a quasi-group. The multiplication table is a Latin square, so not only the rows are permutations, but also the columns are permutations. So if it's a quasi-group quandle, then it's of course connected. There's just a single orbit of the multiplication group. So it's a subclass of connected quandles. And you see that the numbers are kind of similar, which is again misleading for some reason, but still similar observations could be made. Here I compare in the bottom part of the screen. You can compare the numbers with the connected case. So the question is, and in fact, an open problem. What is the upper bound for on the number of connected quandles, and is it quasi-polynomial? Is it really similar to the case of groups, or maybe not? I don't know. To me, yeah, that's a question I'd like to look at in the future. So what we have done so far, okay, so let me talk about now about something that actually we do know. So like yeah, well, yeah. So in the table you can spot a lot of familiar values. Like there's quite a few of zeros. Then you could, if you are a good observer, you could have noticed that for primes, the number is always p minus 2. Yeah, I guess that's all one can observe from the tables. So these are in fact theorems. So the number of connected quandles of order p is exactly p minus 2. That's a result from 2001 by Tinkoff, Soloviev, and Guralnik. The number of quandles of order 2p is almost always 0. Right? There's lots of zeros in the table. So that's the rule. The only exception is 6 and 10. So there are two proofs. One is by Karen, which has never been published, and I have to admit I don't understand it. And there is an alternative proof that was provided by myself with Petr Wojciechowski and Alexander Hubke. And mm, some of those, well, certainly the first one can be explained by another observation that often most of the models are actually affine. Most of the quandles of given size are affine, and whenever you have connected quandles of order p or p squared, then they're actually always affine. So it reduces the enumeration to the affine case, which is substantially easier. So. That's so for order p and p square, it's the result of the guys I mentioned and of Matthias Grania, and also in the table for Latin quandles, for quasi-group quandles, you can observe that there are apparently none of order 2k. Right, so for instance, there is 0 here at 32 somewhere. So sorry, no. Sorry, it's not true. There's not 0, but with yeah, okay, it's not visible from the table, but also there is some result for well, in case of quasi-group quandles of order 2k up to certain order, all of them are also affine, which is something that makes these numbers to be relatively small. And that's actually a result of Tomáš Naď, which you may know for different types of results, but this was his master thesis. I wanted to mention that's the main reason I'm mentioning this, that it's a master thesis of Tomáš, not you, many of you know. So how these results are obtained? Okay, and a lot of these results could have been obtained using the Blackburn representation, which was in fact inspired by a special case that dates back to the beginnings of quantum theory by David Joyce. So we decided to call it Joyce-Blackburn representation. Joyce came up with a special case that works for connected quandles, and Blackburn was able to generalize it. And most of the results that I mentioned actually did not use this framework. The authors usually figured out some more or less ad hoc version of that. So the way I'm going to explain it is taken from a paper by Petr Wojciechowski and Sangyop Yang, who realized that a lot of these results had something in common and formulated the Joyce-Blackburn representation the way I'm explaining it. So. There is a one-one correspondence between quandles on a given set with a given multiplication group. Okay, so you fix a set, for instance, set of numbers 1 up to 10. You fix a group on X, the G, and we are interested in all quandles on that set that have the multiplication group equal to that group, right? And there's a one-one correspondence to certain configuration of elements over this group. So we call it a quandle envelope, and the quandle envelope over group G is a tuple. For each orbit of G, you take one element of the group. Okay. So rho x is an element of the group G, and we get one for each orbit of the action of G. And these elements from the tuple, these rows, have to satisfy two conditions. One is that each rho x is in the center of stabilizer of X. And if you take the union of conjugacy classes of these rows, okay, so this thing means conjugacy class of rho x. So if you take the union of the conjugacy classes, then the union has to generate the whole group, right? So on one side you have quandles, on the other side you have certain tuples of elements of the group, and there's a one-one correspondence. Also, this correspondence has a relatively tame isomorphism theorem. So we can tell when two quandles are isomorphic in terms of quandle envelopes. So two quandles are on a given set with a given multiplication group are isomorphic if and only if the tuples that these quandle envelopes satisfy certain condition, which is maybe too complicated to explain, but simple enough to use. Okay, so in fact, when we want to enumerate quandles, we can choose the groups, the permutation groups up to conjugacy, and these envelopes up to something which is relatively manageable. So you can look at it so that that equivalence can be considered as a group action on envelopes, which is relatively simple to describe, fairly difficult to handle. So what you can do with that? Well, you can handle it imprecisely in the sense that instead of calculating precisely the orbits of this section, you just estimate the numbers. Okay, the number of orbits. So the number of orbits of this section corresponds to the number of quandles up to isomorphism of given size with a given group. So this imprecise handling that's the basis of the results of Blackburn and of Ashford Riordan, and that's the way how they were able to get the upper bounds and the asymptotic behavior for the number of quandles. You can do computer calculations. You can program the whole thing in GAP. You can use the library of subgroups of symmetric groups, the library of permutation groups. You can sort them out up to conjugacy. This is in principle possible up to order 18. So I think GAP has a library of permutation groups up to order 18 in some form, and that can be used. So as long as there are not too many quandles of given size, you can do exhaustive search. So it's like a smart brute force. So that works up to 12. Okay, so the enumeration up to order 12 can be done by smart brute forcing all subgroups of Sn. You can also in case of connected quandles, what does this representation say? So if you have connected quandles, then this means that the multiplication group has a single orbit. So instead of a tuple of rows, you have just a single row, right? So you have a single element row such that it's in the center of a stabilizer. It doesn't matter which one. If you have a transitive group and the conjugacy class of that element generates the whole group, so it's certain configuration in transitive groups. So instead of running over all subgroups of Sn, you can just use the library of transitive groups. And again, GAP contains such a library up to degree 47. So that's the way we can get a classification of connected quandles up to order 47. You can use some theory of transitive groups, and that's the way you can obtain the theorems that I mentioned on the previous slide. Right? So with some group theoretic effort, for instance, you can prove that there are no connected quandles of order 2p because the quandle envelopes would have need to satisfy something which is contradictory to the Owen and Scott theorem. That's pretty much the idea behind our proof of the case of 2p. There are also some theorems which say if the transitive groups is such and such, then it's necessarily solvable, and that's a way to get these results of the sort. If the order is something, then the quandle is necessarily affine. And the final thing I want to talk about is that you can actually handle some special cases separately, and that way you can push the enumeration further. And so what are the limits of the enumeration? Why, for instance, Derek Holt can classify transitive groups up to degree 18, but brute forcing or the smart brute forcing can only yield enumeration of quandles up to order 12 because there are simply too many. So you cannot brute force them because there's too many of them. But as it turns out, most of them are of a particular type. So we can handle that special case separately and then just leave it and the rest to do by brute force. Well, and that's the class of quandles that turns out to be so special is the class of so-called two-reductive medial quandles. And here, just compare the numbers. So in the left column, you have the enumeration of quandles. In the second column, you have the numbers of two reductive medial quandles, and you see that the numbers are kind of similar, and then for convenience, there is the difference, right? So you see that the vast majority of small quandles is actually two reductive and medial. You also see that we managed to classify this class up to until order 16, which is more than we can do in general for quandles. So actually handling this class is in some sense easier than handling the rest. So what is this magic class? And that's the last point I want to make. It actually has something to do with the concept of strong solvability that you may know from the time congruence theory. So uh, a quandle is called n-reductive whenever if you compose any n right translations, then you get a constant mapping. So remember, the left translations are permutations and the right translations are just arbitrary mapping, right? And the left translations are supposed to be automorphisms, but we assume nothing about the right translations. So they seem to be kind of arbitrary mappings. So let's take this seemingly ad hoc condition that whenever you compose n of them, you always get a constant mapping. So we call it quandle n-reductive whenever this happens. Like in particular, two-reductive means that whenever you apply two right translations to an element y and z, you get the same result, right? So it's an equational property. So this simple identity classifies two reductive quandles. What is mediality? Mediality is an identity you might have seen: x y u v equals x u y v. That's not interesting. The interesting, well, the good description of mediality is that it has something to do with affineness. So medial quandles can be composed from affine quandles using certain meshes of affine maps. And here comes a theorem that we were able to prove with Marco Bonato. So a quandle is n-reductive. So this composition property on rat translation, if and only if it is strongly solvable of length at most n, where the strong solvability is the concept from time congruence theory. So how to use that? So for enumeration, we can use the results that we obtained about 10 years ago with Jedlička, Politovská, and Anja Zamojská. There is a relatively efficient way to handle these medial quandles. It's even more efficient in the two-reductive case. So we can turn an isomorphism problem for medial quandles into Burnside orbit counting, and that's how we've got the big numbers on the previous slide. Okay. And I conjecture actually that there are very few non-reductive quandles. Okay. And the thing that I wanted to tell you on the last slide is actually this strong solvability something that matters in enumeration? Is it so that in certain realms like quandles, this strong solvability is the distinction between many models and few models, right? So for quandles, it seems, so the conjecture says that there's in some sense, most of quandles are actually the two reductive ones. And is there any other class which has this behavior where strong solvability would be the property that distinguishes few and many? Okay, thank you for attention.
Thank you. Thanks, David.